Alright, let's dive into something that's honestly mind-blowing. Imperial engineers have just built a reconfigurable photonic quantum chip called Clavina. Now, I know that sounds like a mouthful, but stick with me, because this is a game changer. Here's the hook. Imagine a quantum computer that doesn't need a complete overhaul every time you want it to do something new. That's Clavina. And personally, I think this is one of the most exciting developments in quantum computing in years. Why? Because it tackles one of the biggest headaches in the field, rigidity. Most quantum systems are like single-purpose tools, they're great at one thing but useless for anything else. Clavina, on the other hand, is like a Swiss Army knife. It's reconfigurable, meaning it can adapt to different tasks without needing a hardware redesign. This isn't just a small improvement, it's a paradigm shift. What makes this really interesting is the inspiration behind it. The team at Imperial's Department of Physics looked at modern computer processors and said, why can't quantum systems be more like that? And honestly, it's brilliant. Classical computers have been reconfigurable for decades, but quantum systems? Not so much. Clavina changes that. It combines linear and nonlinear quantum operations in a single system, which is like having a laptop that can switch between being a gaming rig and a data server at the flip of a switch. This modularity is key. It's not just about doing more, it's about doing more without starting from scratch every time. From my perspective, this is what scalability in quantum computing should look like. Now, let's talk about what Clavina can actually do. The team demonstrated its capabilities by tackling two big problems in quantum physics. First, they simulated the Bose-Hubbard model, which is a complex problem in condensed matter physics. What's fascinating here is that superconducting quantum computers struggle with many-body interactions, but Clavina handles it with ease. This isn't just a technical achievement, it's a proof of concept that photonic quantum systems can outperform their superconducting counterparts in certain areas. One thing that immediately stands out is how this could accelerate research in quantum physics. If you can simulate these interactions reliably, you're not just solving problems faster, you're opening doors to new discoveries. The second demo was even more impressive. Clavina generated Gottesman-Kitaev preskill, GKP, states with significantly improved consistency. Now, GKP states are critical for quantum error correction, which is basically the holy grail of practical quantum computing. Previous methods were probabilistic, kind of like rolling the dice and hoping for the best. Clavina removes that uncertainty. This is huge because error correction is what's holding quantum computing back from real-world applications. If you take a step back and think about it, this isn't just about making quantum computers work, it's about making them reliable. And reliability is everything when you're talking about solving real-world problems. What many people don't realize is how much of a bottleneck hardware redesign has been in quantum computing. Traditionally, if you wanted a photonic system to do something new, you'd have to rebuild it from the ground up. Clavina eliminates that. It's like upgrading your phone's software without needing a new device. Ing Dong, one of the co-authors, put it perfectly, the ability to switch in different functional modules enables a single set of hardware to perform multiple functions. This adaptability is going to be crucial as quantum systems grow in complexity. In my opinion, this is the kind of innovation that could make quantum computing sustainable in the long term. But here's the bigger picture, Clavina isn't just a better quantum chip, it's a blueprint for the future. Its modularity and extensibility suggest that quantum processors could evolve like classical computers did, customizable, upgradable, and increasingly powerful. This raises a deeper question. Could Clavina be the foundation for the first truly practical quantum computers? I think it's possible. The fact that it can solve graph problems, simulate quantum systems, and generate entangled states all on the same hardware is a massive leap forward. It's not just about what Clavina can do today, it's about what it enables tomorrow. A detail I find fascinating is the use of fast electro-optic modulators. These are what allow Clavina to switch between tasks so quickly. Photons are notoriously hard to control because they don't interact strongly with each other, but these modulators essentially give Clavina the agility it needs. What this really suggests is that we're getting better at taming the quirks of photonic systems. And that's a big deal because photons have some major advantages over other quantum platforms, like being less susceptible to noise. So, where does this leave us? Personally, I think Clavina is a turning point. It's not just another quantum chip, it's a new way of thinking about quantum hardware. It's scalable, adaptable, and practical, 3 words you don't often hear together in quantum computing. If this technology takes off, we could see quantum processors evolving at a pace similar to classical computers. And that's not just exciting, it's revolutionary. What do you think? Is Clavina the future of quantum computing, or is it just another step in a long journey? Let me know in the comments, I'd love to hear your thoughts.